In this video, I would like to talk about ViTPose paper that currently that I'm recording. It has the state-of-the-art performance for the task of 2D pose estimation on MS COCO dataset. So let's just see that. Before talking about how this ViTPose works, let's just at first talk about the previous attempts that people have tried for utilizing transformers for the task of 2D pose estimation. One of the attempts is called transpose. In transpose, given an input image, at first we should use a backbone, a CNN backbone, to extract some local information from this image. And then we should use a transformer encoder just to understand where are these skeleton key points inside this image. And as the output, it gives us some key point heat maps, which is the location of these key points in this image. The other attempt is token pose, and token pose is kind of similar. At first it uses CNN just to extract some feature maps, but when we have a transformer encoder, in addition to the tokens which are coming from this image, they also include some random tokens which should kind of represent the missing key points. And by missing key points, I mean the occluded ones, which we cannot see them from this image, and we expect the neural network to infer that. Another attempt is HR-former, and in HR-former it also has a combination of transformer blocks and convolutional blocks and some striated convolution just to downsampling and some upsampling, so we need to have a very delicate architecture for the final output. So what we can generally see from the previous attempts is that we either need to have a CNN backbone at the end, or we need to have a very delicate architecture to have our final output. But the question that we can ask ourselves is that, do we need to have these complicated architectures? And ViTPose, to answer that, it only utilizes transformers and nothing else. It has a very simple architecture just to deal with this problem, and let's just see that. And here is what we have for ViTPose. We have an input image, and then we utilize an encoder, which is a transformer. And like all transformers, at first we use position embedding just to make these tokens. And the way that we create these tokens is that when we look at the numbers, it is nothing by h over d times w over d. And what is this d? This is the patch size of the original image. So we kind of divide this image into equal size patches, the same idea that we had in vision transformers initially. And this d, it could be 4 by 4, like 4 pixels by 4 pixels. And then we use some mapping, because initially it is in RGB, it has only 3 channels, but we map it to a higher dimensional C. And that is each token. So each token should represent a patch of image, but in a higher dimension. And following by that, we utilize a multiple layers of transformer blocks until we reach the final output tokens. And transformer block is like what we already know: a layer normalization, a multi-self-attention, a skip connection, a layer normalization again, followed by feed-forward network, and finally a skip connection again. So this is the whole encoder that we have, which is much easier than what we previously saw in previous attempts. And for a decoder, we have two different options. The first option is what they call classic decoder. And in classic decoder, we utilize two different deconvolution modules just to upsample it. Each deconvolution module upsample it 2 times. So initially, if h and w is 224 by 224, we divide this by d, which could be 16. And then by upsample it 2 times by the first one and 2 times by the second one, we overall upsample it 4 times. So it's like we divide h and w by 4 at the end, which is 224 divided by 4, that is 56. So at the end, it's like that we are having 56 by 56 image instead of 224 by 224. But why? Because ultimately we need to have heat maps. And based on the experience on the previous attempts that people have tried, they realized that when we are having 56 by 56 resolution for the heat map, we usually achieve a very good result in case of having 224 by 224 as the input size. So we have 56 by 56 heat map, and the number of heat maps depends on the number of channels. So initially we mapped that three-dimensional RGB into C, which could be very high dimension, but ultimately the number of heat maps is the number of key points that we have, right? So if I have 17 key points, I expect to have 17 heat maps. So this predictor that we have here just maps that high dimension C into 17, for example, which is the number of key points. And we have 17 heat maps that each heat map represents one single key point. And the other option is this simple decoder, as they say, which they utilize bilinear interpolation just to upsample it 4 times here, and then a ReLU and then predictor just to predict these heat maps. And once we have these heat maps, we can kind of estimate what is this joint locations and bones that they connect these joints together. So yeah, that's the whole idea behind ViTPose. But one additional thing that they also did is multi-dataset training. What if we have different datasets that they have different key point numbers and different formats? For example, one dataset could have 17, the other could have 25 or anything. So to take advantage of all of that, we can use a single encoder but different decoders. In the code, we can simply put an if statement that if the sample comes from one dataset, it should go to the decoder 1. If it's coming from another dataset with different key point formats, it should go to the decoder 2, and so on and so forth. And interestingly, if we do this, since we are having more data, we can achieve a better result compared to only having a single dataset for training. So when we look at the experiments and the results, we can see that the others have proposed different variants. ViTPose base, large, huge, and maybe gigantic. That the difference is that they're having different number of layers for sure and different channel size. And here in the staple, they're showing what are the hyperparameters that they have used for training. Nothing that important here. But the second thing that I'd like to point out here in this slide is the simplicity and scalability of ViTPose. So let's just say instead of having Vision Transformer as the encoder, I use ResNet50 or ResNet152. So now if we look at the choice of decoder, which one of them was classic with 2 deconvolutions, the other simple with 1 bilinear interpolation, we can see that for ResNet50 in all cases, or even ResNet152 in all cases, it is worse than ViT counterpart. And the other thing is that when I switch from classic to simple on ResNet, the result becomes much worse, while on ViTPose it becomes a bit worse. That basically means that the encoder that we use when we are using transformers, it gives us a very rich semantic that the choice of decoder is not that important anymore. And by choosing different type of decoders, we always can achieve a very good result. And the next thing is the influence of pre-training data. We all know that when we are pre-training on a large data and then fine-tuning for our task, we should get a better performance, obviously. So here is what they did. At first, they used ImageNet 1K for pre-training and achieved some average precision, which is 75.8. And then they said, if I use ImageNet for pre-training, that basically means that my model needs a huge amount of data to perform very well. But they said we don't want that. What say instead of using 1 million, I use half of it or 1/3 of it. And they tried and achieved a very impressive result. So for COCO dataset, when it is written cropping, that basically means that they only select the one images that have person inside them. So we have 150,000 of images with persons inside them. And if we use that for pre-training, the average precision will become 74.5, which is impressive. It is not that worse compared to what we already had. But when we add AI Challenger dataset, I guess they did a typo error here because cropping should have less dataset volume compared to not cropping. But anyway, if we are having cropping and not cropping while we are using AI Challenger and COCO, by having 1/3 of what we initially had for pre-training, we can get a similar average precision. The other thing is the influence of input resolution. Obviously, as I increase the input resolution, I should get a better result because I have a better granularity for the detail and I can better represent what are the features that they exist in the image. So as I go to the right columns, because of having more resolution, I can have better average precision and average recall. But what is interesting here is that when you look at the second column, you can see that the first column, if you multiply 224 by 224, it is actually having more pixels compared to the second one, 256 by 192. But the second one, even though it has fewer pixels and fewer computation, the average precision and average recall is better. But why is that? Because when we look at the aspect ratio for the second one, it is 4:3. That means that we are having more heights than width, which is kind of similar to the aspect ratio of the people, right? We people usually have more height compared to the width. And maybe because of that, when we are having 256 by 192, we are having a better performance compared to 224 by 224. And the other thing is the influence of attention type. So initially, they used 16 by 16 as the patch size, but then they said, what if I decrease the patch size into 8 by 8? That means I have more tokens, and that means I need to have more GPU memory to store that. And in fact, if I only use vanilla vision transformer, I need 36 gigabytes of GPU memory, which even for A100, which has 40 gigabytes of memory, is not possible because some of it should be reserved for something. So even though they are trying A100, this star means that instead of floating point 32, they are using floating point 60-bit to store them. And by using 8 by 8 patch size, they are getting average precision of 77.4. So now they are interested to decrease the amount of GPU memory and having similar average precision. At first, they used window-based multi-self-attention. So instead of having multi-self-attention on the whole image, they have some 8 by 8 windows and they perform it within that window. If it doesn't make sense to you, just take a look at the swing transformer video that I recorded and I explained all these things in detail. And the other thing is window plus shift, which is actually the swing transformer. And you can see the difference. By having only window without shifting, the average precision drops to 66.4. But when I add shifting, we have 10% more average precision, while the GPU memory is still the same and the gigaflops is still the same. That is how impressive swing transformer is. And the other thing is having window, but instead of shifting, doing pulling. And if I do that, the GPU memory becomes a bit more, but the average precision is the same as the swing transformer. And to be honest, I don't really know how they're doing this pulling instead of shifting. I didn't really understand from the paper. If you understand, please explain in the description. I would be thankful. But what they realized is that shifting and pulling are complementary and we can use both of them at the same time. So window plus shifting plus pulling actually achieves a better average precision compared to solely using shifting or pulling. And the next row, which is combination of full attention and window attention, is ViTPose paper, which I don't really know how it works. It clearly needs more GPU memory and average precision is a bit more than combination of swing transformer and pulling. So what they did finally is that they used a combination of window, shifting and pulling, but instead of using 8 by 8 as the window size, they used 16 by 12. And the average precision on the end became 77.1, which is impressive. So now we have 10 gigabytes of memory less than what we initially had, but the average precision is a bit worse. And the next thing, they try to understand how important each module of multi-self-attention and feed-forward network is for the task of fine-tuning. So they said, if I fine-tune both multi-self-attention and feed-forward network, I reach average precision of 75.8. But if I make the multi-self-attention frozen and only fine-tune feed-forward network, the average precision drops by 0.7%. But if I freeze feed-forward network and fine-tune only multi-self-attention, the average precision will become 3% worse, which indicates that when we fine-tune for our specific task, feed-forward network plays more role than multi-self-attention. This is not true for pre-training, I guess, because multi-self-attention should be more important than feed-forward network. But for the task of fine-tuning, we can kind of freeze the multi-self-attention and only fine-tune feed-forward network if we do not have any adequate resource. And the other thing is the influence of multi-dataset training, as I initially mentioned in the architecture. If we add more datasets with more key point format and different branches of the decoder, on the whole, we can get even a better average precision. And finally, I like to talk about the analysis of transferability, which is knowledge distillation, another interesting field in computer vision, that you can improve the generalizability of your model without adding any data, without adding any new parameters, and just by doing a very cool trick that it is not limited to ViTPose. You can try it on your application and get a better test performance. So assume that we have a teacher transformer, a transformer that has lots of parameters like ViTPose gigantic, ViTPose large, or something like that. And also we have a student transformer like ViTPose base that it doesn't have many parameters, so we do not expect it to be as good as teacher transformer. But our whole goal is to make this student transformer as good as teacher transformer without adding any parameters. And that's where knowledge distillation comes. It says, let's just define this loss function, which they call it OD, or output distillation, which is a mean squared error between the prediction of the student and the prediction of the teacher. So basically, by applying this loss, we already have a teacher transformer which is already trained before, and we only apply this loss when we want to try the student transformer. And hopefully by imitating teacher transformer, we can get a better generalizability. So this loss that we defined, it is not limited to transformers. We can have some ResNet or other architectures. And as long as we have different variants of them, for example, for ResNet, we have ResNet 50, ResNet 152, and different variants. As long as we have a teacher and a student, we can apply that. But there is another type of knowledge distillation, which is kind of limited to transformers. And we can also use that as well. And in this technique, here is what we do. We define a randomly initialized token T, and we append it to a well-trained teacher model and tune it. So we have a teacher model already available, already trained, and we append this token as an additional input token. And we make all the parameters of this teacher transformer frozen except this token that we added at the first. So we want to only change the values of this parameter that we added as the input, and this is the formula that shows what it is done. It says out of all possible token T that we can have for the input, let's just pick the arg min. I mean the one that has the minimum performance. Minimum performance over what? Over this MSE between the output of the transformer and the ground truth. So we add additional token and we train it just by modifying the token, and if the final output is better and it is more similar to the ground truth, I mean that basically means that we trained a well token, and let's call it T star. And next we add this T star to student model, and during training of the student we freeze this token T star, and we say this loss is that the student having this token T star should be very similar to the ground truth. So that's what we usually have for training the student. But in addition to training with changing the weights of the transformer, we have one additional token T star which is frozen, and it exists in the input, which could be some auxiliary information that is coming from the teacher and help us to better predict the final task and be more similar to ground truth. And here are the results. So the heat map is the first one and token is the second one. And if we are using the token idea, the average precision becomes like 0.2% better. And if we are using the heat map idea, which was the first one, the average precision becomes 0.5% better. But it appears that these are complementary, and I can use both of them at the same time, and I achieve 76.6 average precision. Well, the gigaflops is the same. I have a bit more GPU memory, but that's impressive. I mean, we have the same ViTPose with the same amount of computation, but bit better results on the test set. And if we want to compare it with different modules for the task of 2D pose estimation on MS COCO dataset, we can say this, that it is very fast compared to the others. I mean, the speed that it is reported on the speed column is on 800 GPU, so probably for our local computers it couldn't be as fast as 944 frames per second, but still, comparing to other models, we can see how faster it is and how good the performance is as the average precision on MS COCO val set. And the other thing is MS COCO test set, which is more challenging, and they are using a very big backbone, which is ViTAE gigantic, lots of parameters, and it should be a slow. They do not report any frame per second here for sure, but if you look at the average precision, it has the state-of-the-art performance right now, which is 81.1. So yeah, that's all the thing that I needed to say for this ViTPose paper. If you enjoyed it, don't forget to like and subscribe, and until the next video, goodbye.